All right. Okay, so what we're going to look at today, which you can't see, let's see if we can fix that. We are going to review the first and the fourth sections of your book. And I'm hoping that at this point, you may have been able to go in there and take a look at the book. And or if you have the Kindle app, download the Kindle book to your PC or tablet. But this is what your book looks like. Now you can also go straight to OpenStax. OpenStax down here, openstax.org. And then there's a subject list. You pick math and you find the introductory statistics book. So you can open that way. And if you want to create an account in OpenStax, you can do that, and then you can highlight in the book and it will remember what you highlighted. You can bookmark stuff. You have a lot of functionality through OpenStax, but that's your book. Okay. So in chapter 1, it's a lot of terminology. So what we're going to do is we're going to talk about all the key terms that we need for a statistics course. And then we're going to talk about sampling methods. So what you want to use statistics for is data collection so that you can organize and analyze your data. So there are various ways that you can collect your data. We'll talk about that. And then we'll create and interpret frequency tables. So we'll take a set of data and we will start organizing it. And we'll organize it firstly in the form of a table. Okay, so in section 1.1, we're just going to go over a lot of key terms. And again, this PowerPoint is in Blackboard. So if you miss a term or you forget a term, you can always refer back to the Blackboard PowerPoint. Okay, what is statistics? Statistics is the science of collecting, organizing, analyzing, and interpreting data in order to make decisions. And when I worked back in industry, I would say, and I say this to people all the time, why are you collecting the data? If you're not going to make a decision based on the data you're collecting, then you're probably wasting your time. There needs to be a reason for you to collect data. The goal of statistics is not to perform numerous calculations using the formulas, but to gain an understanding of what your data is, what it looks like. Are there trends? Does it fit what you think it should fit? Is it doing what you think it should have done, but it's not? Are there things that are different from what should be normal for the set of data? All that kind of stuff. Okay. We're going to do our first statistics problem. Woo! So I'm going to go around the room, starting here, and you're going to tell me how many hours you slept last night. So this is our first. Well, if it's 12, that's great. If it's 1, then, or if it's 0, that's okay. Okay, now the limiting end of this is 5. So if anybody slept less than 5 hours, you're going to be an outlier. You're not going to be in our data collection. Okay, so just tell me on average how much you slept. Now I could look up on my app. You know, I have one of those apps. My bed is a Sleep Number bed, and it tells me how much I slept.
Do you like your Sleep Number bed?
I love my Sleep Number bed.
I've never slept in one, but it seems cool.
Okay, I slept.
Do you have it like on the hard setting or the soft one?
I have it kind of in between. I slept 7 hours. So I'm going to put a dot. Okay, approximately how much did you sleep last night? We're going to start right here.
2.
2? Oh, gosh, you're off the chart. Let's make a. You need to get more sleep. How about you?
5.
You need to get more sleep too. How about you? Good for you.
Good job, Allie.
How about here?
5.
2.
Yeah, buddy. I'm not
I
alone.
am also in that 2 category.
Hey, that's all right.
Are you at 2 also?
Yeah, I am.
Okay, let's have some advice from a woman my age. You need to get more sleep. All right, where are we at? Back row. Oh, did we get you? No.
I'm 6.5.
6.5. Back row.
6. 6.
7.
That's how they have like 12.
You say 6? Okay, right here.
7.
7?
8. 6.
4? I'm gonna have to make this longer. How about you?
4.
4?
6.
8.
So do I win a prize?
Pardon?
Do I win a prize?
You do. You're the most rested and alert, right? Okay.
That's impressive too.
I think we should get a prize. I don't think so.
What does this, I mean,
I like that one.
just looking at this,
I'll say we're getting some good sleep.
you think so?
should get a little less homework for that.
Hey,
A little less over for that.
now we're thinking hard.
Is it my fault you only got 2 hours of sleep last night? What interpretation can you make from this?
There's a lot of people that don't get much sleep at night.
Sucks being a college kid.
That pretty much sums it up. Is that untypical for college students? Okay, let me ask you this. There are quite a few student athletes in here, correct? So how did you trend compared to others?
We don't get much sleep.
You don't get much sleep? Okay, so that may be some of these 2 to 4s. 2 to 4s, any of you the 2 to 4s, do you have to work at night?
Negative.
Negative? You just didn't go to bed, okay.
I just wasn't tired.
So do you think this, okay, let's look at this. Do you think this would be different for 20 people that were my age?
Yes.
Oh, yeah, you think? Even though at my age, we require less sleep than at your age? Younger people require more sleep. That's why I always, when I get up at 7:30 in the morning and sit in front of a bunch of 18-year-olds at USACON High School, I say, it's insane to make high school kids get up at 7:30 in the morning. You just don't work that way. But that's typical of people who are in college, probably. I mean, people that are younger. Teens and early 20s, that's kind of typical of that age group. So if you looked at a group of people my age, do you think it would tend toward more the 7 through 8, maybe? I don't know. We
I
could.
don't know, because I'm 32 and I was 5, so.
Yeah, yeah. So that might be something, if you wanted to investigate, that might be something to look for in trends. Is it? And there certainly have been social psychologists that have looked at this, but it's something that would be interesting to look at. So do you think an English Comp 1 class would be the same?
Like from here, like school-wise?
Would they have the same distribution of sleep hours, do
If
you
they're the
think?
same age as us, probably.
You think they'd have less?
No, they have more.
You think they'd have more? Why would you think they'd have more?
Well, maybe their class will start at 12:30.
Well, maybe. But what if it started at 9:30 like this one?
That's probably the same.
About the same? So what'd you say, Nate?
Probably the same.
About the
English class
same?
is kind of a lot less demanding than a math class, so,
It's a lot less demanding.
yeah.
So if they don't have any math classes, maybe they, I don't know, do they get more? Maybe, I don't know. Something to investigate, something to look at. English Comp 1 is a freshman class. This is a sophomore level course. Do sophomores get less sleep than freshmen? Oh.
I just don't be getting sleep, honestly.
So second semester sophomores, how much sleep do you get? You're getting ready to graduate. Where did your data appear to cluster? We talked about it appears to cluster. I mean, we got quite a few at 6. So it appears to cluster at 6, but seriously, 2 to 5, what have we got? 3, 5, 8. So it appears to cluster toward that lower end for this particular class. And that may not be typical for every class on campus, obviously. But for this class, last night, that appears to be the trend. Okay, so the questions we ask helps us to analyze and interpret data. With this example, you've begun your study of statistics. Now, wasn't that fun? Okay, the first type of statistics we're going to discuss are called descriptive statistics. So when you take a set of data and you organize it and you summarize it, that's descriptive statistics. And they show 2 ways that you can organize data. That's using charts. And charts are a wonderful way to organize data because they give you a nice picture representation of what your data is doing. So we have bar charts over there, which we will do later. And we have a pie chart, okay, which we will talk about later. The 2 ways of summarizing data are by graphing it and then by using numbers. So you could, for example, in this class, I could take that set of data that we just gathered, right? We drew a picture of it, little dot chart, but could I take those numbers, add them up, and divide by the total number in here and get an average?
Yeah.
Yes, I could. So I could also describe that data by the average. Now, in short order, we will also look at how much the data varies. So the lowest amount of sleep was 2 hours. The highest hours of sleep was 9 hours. So we already see that there's a pretty good range in our data from 2 to 9 hours. So we could also look at how much the data spread is. So there's lots of ways we can look at what our data is doing descriptively. Inferential statistics, on the other hand, after you have studied probability, which we will, and probability distributions, which we will, you will use formal methods for drawing conclusions from good data. And yes, there is bad data, a lot of it. The formal methods are called inferential statistics. Statistical inference uses probability to determine how confident we are that our conclusions are correct. The goal of statistics is not to perform numerous calculations. As a matter of fact, you're not going to. You're going to let your calculator do the work for you, and it will do a lot. Your job is to understand why you're using your calculator the way you are. That's your job. Okay? Probability is the mathematical tool used to study randomness. It deals with the chance or likelihood of an event occurring. if I take a coin, which I don't have one in my pocket, if I had a quarter and I flip that quarter twice, I may or may not get one head and one tail. Now, if you think about this, if the coin is fair, that means it's completely balanced. Should you get the same likelihood of getting a head or a tail?
It's 50/50.
It should be 50-50. It should be. But on a small sample, flipping it twice, you may or may not get one head and one tail. Now, if you flip it 1,000 times, probability says that if it's a balanced coin, you should get 500 approximately heads and 500 approximately tails. Okay, now she keeps saying balanced. Every Super Bowl, they flip that big thing and I say, did anybody check to see if that's balanced? You know, it's one side have exactly the same probability of the other side coming out. Because I think US quarters are not perfectly balanced, if I remember correctly. We might Google that. Okay, all right. So statistics is based on the theory of probability. The theory of probability began with the study of games of chance, such as poker. Predictions take the form of probabilities. So you told me the chance of a head coming up is 50-50, 50%. To predict the likelihood of an earthquake, of rain, or whether you will get an A in this course, we use probabilities. The probability of rain this morning was 65%. I don't think it rained. That simply means that on a day with these particular conditions, 65% of the time it rains. Okay. Doctors use probability to determine the chance of a vaccination causing the disease the vaccination is supposed to prevent. A stockholder uses probability to determine the rate of return on a client's investments. You might use probability to decide to buy a lottery ticket or not. In your study of statistics, you will use the power of mathematics through probability calculations to analyze and interpret your data. Okay, key terms, population. Your first key term. In statistics, a population is who we are interested in studying. So you can think of a population as a collection of persons, things, or objects under study. So it's the stuff that we want to look at. So let's determine the population. We want to know the average mean amount of money first-year college students spend at I can never say this. Jacinto.
Just say San Jac.
Sanjay. I practiced it yesterday and then my mouth doesn't work. San Jacinto, right? Jacinto? St. J College school supplies that do not include books. We randomly survey 100 first-year students at the college. 3 of those students spent $150, $200, and $225 respectively. So what's your population?
3 students.
What's that?
So 3 students.
100 students.
What's your population?
You don't know because it's just saying there's 100 of them. It doesn't say the rest of them.
So the 100 of them is important. We'll talk about that in a minute. But what are you interested in finding out?
The amount of money,
The amount of money from whom?
first year college students.
First-year college students. So what's your population? First-year college students. And you're interested in the amount of money they spend, or aren't you? So your population is your first-year college students. Because that's who you are interested in looking at. Now the 100 and the 3 numbers there are going to have definitions here in a minute. But overall, you're interested to know what they spent. first-year college students at San Jay College. Okay? So what's a sample? A sample is a portion or subset of your population. So to study the population, we select a sample. The idea of sampling is to select a portion or subset of the larger population and study that portion, the sample, to gain the information about the population. Fact of the matter is, we'll discuss this again later, it's frequently impractical or expensive to look at an entire population. So we can pick representative samples from our population to represent the population. Okay? So now, what's your sample? What's that?
100 college students.
The 100 college students. So now, if your population is all the first-year college students, and we are going to survey 100 of them to represent our population, then they would be our sample. Now, for some reason, your book says the answer is, could be all the students enrolled in one section of a beginning statistic course. Well, that may be true if that's where that 100 people came from. But the fact of the matter is, if you survey 100, wherever they came from, that would be your sample. And they may come from one section of a statistics course. They may come, well, we'll talk about that later. Okay, now what's a parameter? P, population. So the word parameter represents something applying to a population. A parameter is a number that is a property of the population. Because it takes a lot of time and money to examine an entire population, sampling is a very practical technique. I mean, what are some things you could use to describe your population? The number of items in your population. That would be a parameter. If you found the average of some attribute in your population, that would be a parameter. Okay, so determine the parameter. We want to know the average mean amount of money first-year college students spend at San Jay College on school supplies that do not include books. We randomly survey 100 first-year students at the college. This always bothers me because I'm the one that did that. At the college. 3 of those students spent 150, 200, and 225 respectively. So what's the parameter?
The average amount of money.
The average amount of money that all first-year college students spent. So it's for the entire population, not the average of our 100. The entire population. Okay. What's a statistic? So a parameter goes with population, statistic goes with sample. Isn't that clever? A statistic is a number that represents a property of your sample. For example, if we consider one math class to be a sample of the population of all math classes, then the average number of points earned by students in that one math class at the end of the term is an example of a statistic. So parameter, population, statistic, sample. Okay, so what's your statistic? Determine the statistic. I'm gonna sit. Been a long week.
The average
Average of what?
amount of money spent.
By who?
The first year college student.
It's a statistic. So what are you going to find the average of?
The 100
The 100 students. So a statistic is a value associated with your sample. So we're sampling what, 100 students? And from that sample, we can find the average of the sample. So that is a statistic. Okay, variables. A variable in statistics is denoted by a capital letter, such as capital X or capital Y. It's the characteristic of interest for each person or thing in a population. Okay? Variables may be numerical or categorical. Numerical variables take on values with equal units such as weight in pounds or time in hours. Categorical variables place the person or thing into a category. If we let capital X equal the number of points earned by one math student at the end of a term, then X is the numerical variable. If we let Y be a person's party affiliation, then some examples of Y include Republican, Democrat, and Independent. So in our example, the capital letter X represents the number of points earned by one math student, and the number of points earned by one math student could take on several different values from 0 to 100 theoretically. And if we let Y be the variable representing someone's party affiliation, then the values that Y could take on, it's a variable, right? So it could take on various values. Some of the values it could take on would be Democrat, Republican, Independent. What other party affiliations do we have? So Y is a categorical variable. We can do some math with values of X, or if we define our variable X to be the number of points earned by one math student, we can do math on that. We can do math on numbers. However, it makes no sense to do math on categorical variables. It doesn't make sense to find the average of party affiliation. As soon as you say, I'm going to find the average number of Democrats, what have you done? You've changed your variable from categorical to numerical. As soon as you say, I'm going to count the number of Democrats and find the average, the number of these people and find the number of Democrats, you've made it numerical. I can't talk. Okay, determine the variable. We want to know the average mean amount of money first-year college students spend at Sanjay College on school supplies that do not include books. We randomly survey 100 first-year students at the college. 3 of those students spent $150, $200, and $225. So what's your variable?
School supplies.
School supplies, not only school supplies, but how much you spend. Would that not be correct? What are you interested in? You're interested in the average number they spend. So your variable would be the amount they spent. That's what you're interested in looking at. The variable could be the amount of money spent, excluding book on one first-year student. Let X be the amount of money spent, excluding books, by one first-year student attending Sanjay College. So this is how we represent variables in statistics. We describe them. So we say capital, whatever letter we're using, equals, and then we describe what the variable represents. And this variable can take on numerous values depending on the student. We have 3 values that this variable took on, right? But it could take on numerous values. Okay? Data are the actual values of the variable, which I just gave you the answer to the next problem. They may be numbers or they may be words. Datum is a single value. So what's the data? I think I just gave you the answer. The data is the values that your variable can take on. So what data do we have in this problem?
150, 200, 225.
You got 3 pieces of data, don't you? You know that 3 students spent 150, 200, and 225. So that is the value that your variable can take on. Since it's the value your variable can take on, it's your data. Okay. Oh, I'm doing well. So we're going to talk about experimental design and ethics. You know, if there could be, I'm not sure there's a branch of mathematics where you can be more unethical than statistics. You can cheat your way through stuff like you wouldn't believe. So it's my opinion that every time you see data being in the news, the first thing you should do is look at it with healthy skepticism. All of it. I have seen some, and the other thing is that statisticians, researchers are so eager to publish, because nowadays, as soon as you get data, you want to publish it, that they publish without any analysis. Well, they might analyze the data, but they don't understand why their data is doing what they're doing, but they publish it anyway. And I think that's a problem. I saw a study a couple of years ago, and I read, well, that's alarming. It was a study about care of new mothers. And the data was alarming, and the data was real. As far as I know, the data was real. It was taken legitimately, collected correctly. But the conclusion they drew was alarming, but they had no explanation for the conclusion they drew. So I had a problem with that. So, for example, an experiment. Does aspirin, so another word, experiment. Does aspirin reduce the risk of heart attacks? Well, there's been studies that say yes and studies that say no, so I'm not sure anymore. Is one brand of fertilizer more effective at growing roses than another? Is fatigue as dangerous to a driver as the influence of alcohol? Questions like these are answered using randomized experiments. Could you conduct an experiment to see if fatigue is as dangerous as alcohol? Could you do a safe conduction of the experiment to see if it's as dangerous? We will look at important aspects of experimental design. Proper study design ensures the production of reliable, accurate data. The purpose of an experiment is to investigate the relationship between 2 variables. When one variable causes change in another, we call the first variable the explanatory variable. The affected variable is called the response variable. In a randomized experiment, the researcher manipulates values of the explanatory variable and then measures the resulting changes in the response variable. So that's what a randomized experiment is. So we change the values of the explanatory variable and see what happens to the response variable. The different values of the explanatory variable are called treatments. An experimental unit is a single object or individual to be measured. So there's lots of definitions in that slide. So let's say you want to investigate the effectiveness of vitamin E in preventing disease. You recruit a group of subjects and ask them if they regularly take vitamin E. You notice that the subjects who take vitamin E exhibit better health on average than those who do not. Does this prove that vitamin E is effective in disease prevention? Not necessarily. And this is where statisticians get in trouble. They assume that a relationship is a cause and effect relationship. It may not be. There are many differences between the two groups compared in the addition to vitamin E consumption. So, for example, people who take vitamin E regularly may be healthier in general. They may exercise, diet, because vitamin E supplements are frequently taken by people who care about their health. So any one of those factors may be affecting the person in the study's health. So in this described study, this does not prove that vitamin E improves your health. So these variables, like that they exercise more and they watch their diet more and all those kind of things, are called lurking variables. So variables that may affect your experiment other than the variable you're looking at are called lurking variables. In order to prove that the explanatory variable is causing a change in the response variable, it is necessary to isolate the explanatory variable. The researcher must design her experiment in such a way that there is only one difference between groups being compared. This is called the planned treatments. This is accomplished by the random assignment of experimental units to treatment groups. So you have a bunch of objects, people, subjects, and you randomly put them into groups. When subjects are assigned treatments randomly, all the potential lurking variables are spread equally among the groups. At this point, the only difference between groups is the one imposed by the researcher. Different outcomes measured in the response variable, therefore, must be a direct result of the different treatments. In this way, an experiment can prove a cause and effect connection between the explanatory and response variable. Okay, so this is an example that came out of a statistics class here at Redlands. So I had a student a couple of years ago that wanted to do an honors. She wanted to do an honors project, and she worked at a grower. And so she was going to compare two different fertilizers. And I said, okay, if you're going to do that, if one fertilizer is better than the other for the plant, what are you going to have to do? You're going to have to do a lot, because you have to remove all the lurking variables. So you have to make sure you have the same type of plant that's growing, that they have the same lighting, all the other things has to be identical. The only difference in these two plants is what fertilizer you put on them. Everything else must be identical. So if anything else is not identical, if you have a lurking variable, it can affect the experiment. So she was going to have to be very careful about how she looked at this, right? So if you're going to do that kind of experiment, that is what you have to do. Okay, the types of studies, there are retrospective studies, a study in which data from the past is examined all the time. So data may be taken to look at, does a particular medicine help in reducing the number of heart attacks? And then they notice maybe while they're looking at the data that this group that was taking the drug actually had less instances or more instances of a type of cancer. So they take the data and they go back and look at it again and reanalyze it in that respect. Okay? Observational study is a study in which data is collected without anything being done to the subjects. So I could do an observational study in this room simply by observing, not doing anything to you. How many of you have computers out? I'm not complaining, I'm just saying. I could maybe look at, well, maybe not all of you, some of you have hats on. How many of you have brown hair? So I could do those kind of observations, couldn't I? And I could maybe draw conclusions from that. The number of people who have computers out, pay attention, but pay attention less. I don't know. People with brown hair are smarter. I don't know. You could do something silly. That's true. That's true. I got blonde hair. Experiment is a study, and this is my hair color, folks. No color there. A study in which a treatment is applied and responses are observed. So an experiment is where you take the groups, you apply the treatments, and then you examine the responses. Okay, a controlled experiment, when participation in a study prompts a physical response from a participant, it is difficult to isolate the effects of the explanatory variable. To counter the power of suggestion, researchers set aside one treatment group as a control group. This group is given a placebo, a treatment that cannot influence the response variable. What's a placebo? Yeah, it's fake. It doesn't do anything. But a placebo can have an effect on a patient, can it not? Power of suggestion is very strong. So the control group helps researchers balance the effects of being in an experiment with the effects of the active treatment. Of course, if you are participating in a study and you know that you are receiving a pill which contains no actual medication, then the power of suggestion is no longer a factor. If you know you're getting a placebo, you know it's not going to be doing you any good. So you cannot know that you are the group receiving the placebo. So it's called blinding. Blinding is a randomized experiment and it preserves the power of suggestion. So that means that you don't know what treatment you are receiving. When a person involved in a research study is blinded, he does not know who is receiving the active treatment and who is receiving the placebo. A double-blind experiment is when neither the participants in the study and the researchers do not know who is getting what. So somebody else is choosing which group gets the treatment and which group gets the placebo. The researcher doesn't know. So their data is not affected by any preconceived notions at all. Okay, so kind of skip through this. This guy's name is Diederik Stapel. And when this slide was made a couple of years ago, he had 55 papers that he authored that were removed from journals. It's now up to 58. So here's the example of this push to publish. He had published hundreds of papers. And he wasn't a very, he's born in 1966. He's still alive. So he's, how old is that? 55? He's 55 years old. And has, this all blew up in like 2011. So he had published all these papers and he had falsified his data. And he had people review his data, review his papers, and publish them anyway. And he was published in many, many well-known, well-established research journals. And it was all fake. And the way that people found out was he published a paper and you may have heard this because I remember when this paper came out that said that people who eat meat are not as kind as people who don't. So carnivores were meaner than vegetarians. That's the conclusion of his paper. And somebody went, what? Finally, somebody went, what? And it was completely fabricated. He fabricated the data to fit his desired outcome and then published. And he says that the reason he did this is because he didn't like messy data. So if the data didn't reach the conclusion he thought it should reach, he fixed the data. No. Okay, pardon my French. Have you ever heard there are lies, damned lies, and statistics? So we're like on top of the totem pole. Lies, damned lies, and statistics. So he's like the most egregious example we've had recently, but it happens all the time. So whenever I see a research study come out, I go, okay, how did you collect your data? And if that's the other thing, if you're ever involved in research and the researcher will not supply you their data, there's something wrong. They should be willing to give you the raw data for you to analyze. And if they're not, there's something wrong. That's why I was saying earlier, I'm not, I can't, you can't follow the data of every researcher, but it gets frustrating as a consumer of data when so many studies come out saying one thing and 2 years later it says something else. And there's a big joke about that, you know. Well, it was bad for us last year. This year is good for us. Well, but that's the reality of the situation when you look at being a consumer of data. So for example, coffee was really, really bad for you. And then, okay, 3 cups of coffee for you is actually good for you. And now I'm not sure exactly where the research is, but you know, it's one of those, it frustrates me as a consumer of data. All right, when a statistical study uses human participants, as in medical studies, both ethics and the law dictate that researchers should be mindful of the safety of the research subjects. The U.S. Department of Health and Human Services oversees federal regulations of research studies with the aim of protecting participants. When a university or other researcher institution engages in research, it must ensure the safety of all human subjects. For this reason, research institutions establish oversight committees known as institutional review boards. All planned studies must be approved in advance by the IRB. Key protections that are mandated by law include the following. Risk to participants must be minimized. I'll let you read through that. Participants must have informed consent. They must consent in writing, and the data collected from the individuals must be guarded carefully. I was in 2 conferences this summer. The conferences were sponsored by a grant from the U.S. Department. I can't remember, what's it called? Science and something, I don't know what they're called. But it's by the U.S. government. It's a grant from the U.S. government. And they are doing research. I don't know what kind of research they're doing. I should ask them. But I had to sign consent that I would be in the conference and that they could take my picture and they could record the video of the Zoom. Sorry about that. Okay, so here's another one that kind of bugs me. Not that if any of you are anti-vaxxers in here, just don't listen to me for a minute. So several years ago, supposedly there was a study that came out that said, and was it the MMR vaccination caused autism? Do you know that's completely and totally 100% false? There has never been a study that says any childhood vaccination causes autism? Never, ever, ever has a study ever said that. None. No, no data, nothing. You know where that came from? So the guy that did the research was at a conference, a news conference, and they kept bugging him. Doesn't vaccinations cause autism? Doesn't it? And somebody was bugging him. He goes, well, I don't know that we can say that, or something like that. He just kind of blew it off. So the conclusion was that he said that it caused autism. His research does not support that one iota. But it blew up, and somebody, who's the Hollywood gal, whatever her name was.
Alicia Silverstone?
She's one of them, but I'm thinking of Jenny McCarthy, whose son is autistic. She decided it was because he had been vaccinated. And she had the world's ear. At the time, she was something. Does anybody know who Jenny McCarthy is? See, she's not something anymore, but she was then. And she got the world's ear, and there off we went. And there is no research, no scientific study that supports that one iota. FYI. Google it. Okay. Researchers want to investigate whether taking aspirin regularly reduces the risk of a heart attack. 400 men between the ages of 50 and 84 are recruited as participants. The men are divided randomly into two groups. One group will take aspirin, the other group will take a placebo. Each man takes one pill each day for 3 years, but he does not know whether he is taking aspirin or the placebo. At the end of the study, researchers count the number of men in each group who have had heart attacks. So, identify the following values for the study. What is your population? What is your sample? What are your experimental units? What's your explanatory variable? What's your response variable? And what's your treatment? Okay, so what's your population?
The 400 men between ages 50 and 84.
Well, I would argue that's not the population.
Or is
Wouldn't
it
it
all
just be
men?
the men between 50 and 84?
So all men between 50 and 84 would be the population. Now, what did you just describe?
Sample.
The sample. So if the population are all men who are ages between 50 and 84, and we look at specifically 400 of them, that would be our sample. Okay? So what's your experimental units?
Two groups.
The two groups. The people taking, the men taking the placebo or the aspirin. Okay? What's your explanatory variable?
Aspirin.
And or
The placebo.
the placebo, because they're two groups are receiving medication. One is a placebo, one is aspirin. So your explanatory variable is the pill they're getting. Okay? What's your response variable? Whether they have a heart attack or not. Okay? What's the treatment? Well, in this case, the explanatory variable is that they're receiving a medication. The specific treatment is they're getting either what? A placebo or aspirin. Very good. Good job. Okay, we're going to cover just a smidge of this. Just a smidge. Okay. What little smidge do I need to cover? I had written it down, but do I remember? Actually, I think we're good. I think we're good to go. Are there any questions? That was hard, wasn't it? Sorry about that. Any questions? All right. Have a great rest of your week. We'll see you Tuesday.
wanted to let you know, I don't know how big of a deal it is, but since I've had surgery